Okay, we're starting up section 4. It's kind of a extension of section 3. So this is a sequence of transformations. The first one was just sequences of transformations that included dilations. This expands upon that a little bit, and the targets are pretty similar. This one we're gonna have some more mapping involved. The difference between section 3 and section 4 being that section 3 just kind of focused on transformations that preserve distances and ones that do not. Section 3 was kind of just to help you identify that dilations don't preserve distances where the rest of them do. Okay, this one is going to help you actually put that to use a little bit more in detail, saying that I'm going to be able to map, so these are pretty similar. One is like the opposite of the other. Just saying that I'm given, this one's saying given I can represent a sequence of transformations that will map the image onto the preimage, right? And this one's saying I can describe a sequence of transformations that will map the image onto the preimage, right? So the difference between these is like, if I'm given a description with either the words or the algebraic description, I can write it on a coordinate plane. This one is saying is if I'm given the coordinate plane and the images, I can write down the word description or the algebraic expression. So kind of the opposites. Okay, and then again, identifying what do or do not preserve distance is kind of going off of section. This is pretty much section 6.3. And then describe that I can use a description of sequence transformation to determine if it did not, or as I guess again 6.3. Okay, so just a repeat of 6.3. I'm gonna revisit the commutative property. I don't know if I talked about that in 6.3, but if I didn't, I'm going to talk about it in 6.4. Commutative property, just a real quick understanding of it is if a series of transformations can be done in any order, like say I have a transformation 1 is like a translation, and then transformation 2 is a reflection. Say for instance I could do those in order, and then if I did like 2 then 1 and I got the same result, then the commutative property exists. But if I did not, then the commutative property does not exist, and we should be able to see at the end of the lesson here the difference between those two. Okay, and then some major questions that we're going to try to answer, or that you should be thinking of during all this, is like what transformations occurred to map one shape on top of the other. Right? Remember, mapping is like if I just kind of like transpose one shape on top of the other, that's what mapping is, right? What transformations include a sequence of transformations that didn't preserve distance. So when did a dilation occur? I don't know why they got so complicated, right? So when a dilation occurs, distance is not preserved. That's all you need to remember. Okay. So how can orientation for the vertex points on a figure help determine the transformations that took place? Remember, that's like when we orient the image in a certain way, right? So if I have something pointing this way and then another one pointing, see if I can, I did it the same. Another one pointing like this way, right? Right. Orient it. This is pointing this way. It's pointing this way. If I orient them the same, getting the transformations, helping them determine. These are the vertexes, right? Remember the points, the ends of the angles, making them all aligned the same way. That'll help you determine which way everything is. determine what transformations took place, right? And then so does coordinate, especially before you do a coordinate pair comparison there. So, all right, so let me go ahead and pull up my first set of notes here, and we'll get going on this. All right, so here we go. So say we have, it says, oh, let's say we start with a, I don't know, polygon. And our quadrilateral, our initial one is let me zoom in here a little. Zoom in even more. There we go. Yeah, that'll work. All right, so our initial quadrilateral is a quadrilateral that starts with this. It's unnamed. This goes to this, and it goes to here, and then it shoots over to like 2, 4. Shoots over to 2, 4, like this. Yeah, and then I don't know, and then it meets back up. That's a good one to start with. All right. Okay. So now let's say that the first transformation. What happens if we apply a transformation with the algebraic description of, it's hard to look at my paper and then look at the screen and see what's going on. Okay, first transformation that we're going to apply is to this one. So this is the pre-image. So transformation number 1. Yeah, there we go. Transformation number 1 will be x comma y of, do an x and a y. So the x's and the y's stayed the same, but we are going to swap the x values. All right, so what does that look like? Well, that's going to be a reflection across the x-axis, right? So we're going to go ahead and do that. It's pretty easy to do. 1 and then 2, right? And then this one goes over. Oh, this would be -1, -1. That always throws me off with these lines of. So these guys go here. These stay all the same x-axis, right? And this one goes down here, and then this point goes over here, rises over here, over there. Right, so then they're going to be just like this. Okay, so that is my reflection across the x-axis. It looks a little funny because these numbers here kind of to provide an optical illusion to that. Okay, so then what happens if I were to take this next one here, one I provided, and then I did something like this. Okay, well, what is that? Okay, well, I'm going to make a actual algebraic point description table for that one. All right, so my blue point my blue points. I'll call this one, I'll just call this one A, B, C, and D. So I have A, B, C, and D. And my initial point was -1 and 3. And then I have -1 and 1. And I have -2, -2 and 0. And then I have -4 and 2. -4 and 2. Right, so my new, if my algebraic expression for this one is going to be -x, -y, then I'm going to take the -x value and I'm just going to change all these to positives. 1, 1, 2, 4. Change all these and flop them around. The signs will become negatives. -3. Oh, why am I making that? It should be a different color. -3. -1, 0, -2. Well, these should have been all this color. Okay. All right, so now I'm going to go ahead and plot all these. 1, -3. 1, -1. 2 and 0. And then I have 2 or 4 and -2. 4 and -2. Okay, and I take all these ones and I connect them together here. And that is my, oh, there you go. That's what it looks like when it's done. All right, so what type of transformation was that? If you remember, a -x, -y, that is a rotation of 180 degrees. I guess it would help if I labeled these, huh? So -1, -1, -2, -4, this would be -1, -1, -3, this is A, this would be B, that would make that one D, and that would make this one C. Right, so that's a 180 degree rotation. So this was a 180 degree rotation. 180 degree rotation right after a reflection. Okay, so let's see if that is commutative. So we're going to start and we're going to do a, what would happen if we took this orange one here and we did a 180 degree rotation of that. All right, so if we rotated this first, we did a 180 degree rotation of this, it would end up over here. Okay, and then if it would end up over here, right, and then if we did a reflection across the x-axis, so the y-axis, it would end up over here. So let's see if it actually everything lines up right. Okay, so our points, we'll call this, this would be D here. So these are primes, by the way. Prime. Technically, these are double primes, and these would be primes. Okay, that would be D. This would be A. Yeah, it's B. So now let's do this. These are all double primes. These are all double primes. Alright, so now in this scenario, let's use purple to be our first transformation. Okay, our first transformation would be a 180-degree rotation of the blue one. Okay, so our orange points are 1, so A, B, C, and D. Okay, our A point is 3 and 1. Our B point is 1 and 1. Our C point is 2 and 1. Our A point is not 3 and 1, it's 1 and 3. 1 and 3. 2 and 1 is 4 and 1. Okay, and then our transformation points would be negative x, negative y. I need to move that up some more. Negative x, negative y. Okay, so they would be, everything's going to turn negative, which makes sense because it would end up in this quadrant. Okay, so negative 1, make all these negatives. Everything was positive, it's all going to be negative. 1, 1, 2, 4, 3, 1, 1, 1. That's not right. 4, 1. This should be 4, 2. 4, 2. 4, 2. 3, 1. 4, 2. One of these is a 0. Yeah, C is a 0. I rushed that up a little bit. Alright, here we go. Alright, so now let's plot the purple numbers here. Alright, so our A prime is going to be negative 1, 3. Negative 1, 3. And that's our purple A prime. Okay. And then our B is going to be negative 1, 1. That's B prime. And our C prime is going to be negative 2, 0, which is right here on C. Negative 2, 0. C prime. And then our D is on 4, negative 2. 4, negative 2. So that's going to be D prime. Connect them all together. And there we go. And now you can see that if I were to reflect this, which is the, how did I put 3 up here? Should have been the second one. This is the second transformation. So the second transformation of this one, so this was the first transformation of our second series. And then our second transformation would be the burgundy one. It would be the reflection. This is a reflection. Our second transformation would be the reflection. This is the rotation. It was the first transformation. Okay, so then it would be pretty obvious here that is if we reflect it across the y-axis, right, it would land in the same spot for each one of these. This one would land here. This one would land here. This one would land here. And this one would land here. So this series of transformation is commutative, because if I did 1 or 2 in any order, I ended up right here. Okay, whether I went from here to here, and then from here to here, or from here to here, then here to here, I still ended up here. Okay, so that's what this whole thing was about. Okay, I'm going to pause and move on here in a second. All right, so here is some work from the homework assignments that I use as examples that closely mirror your practice examples. We're going to work through this one. All right, so we have HGK as a result of some transformations of QTSR. Right, so this is the final image after 2 transformations. Right, and this is the initial image. This is the pre-image, and then this is like the intermediate image. Right, this one's like the intermediate image. So it goes initial 1, and then 2. Initial 1 and then 2. Okay, so that's what's going over here first, right? This one isn't labeled because it makes it more challenging to figure out from where this one went to this one. Okay, so describe the first transformation. Well, if it's not obvious to you, this was a reflection across the y-axis, and if you can't figure it out, you do a simple point comparison. Okay, we grab a point number off of this axis. Let's just label these arbitrarily. I'm going to label it, what I'm using this as purple. I'm going to label this as A, B, C, and D. Okay, just to be able to mark it. Okay, so I'm going to, my initial image, I'm going to make sure I'm going to pick 2 points that don't have the same absolute value. So I guess yeah, I'll click S and B. So S is my before my transformation. So it's 5 and -2, right? And then B is my after my transformation, which is 5 and 2. Simple point comparison shows that my algebraic, the tail end of my algebraic expression, which is my point comparison, right? My x has stayed the same, right? And my wait, sorry, I got that backwards. That didn't make sense. Right, sorry about that. I caught it during my algebraic expression evaluation. I do that a lot. All right, so it's actually, my s's are my x value is -2 and 5, and my b value is 2, 5. Right, so my algebraic expression is my x and y values didn't swap. They stayed in the same column, but the value of my x swapped in sign, right? So this is -x, y, and that is a reflection, the tail end of a reflection across the y-axis. I spelled axis wrong. It's an extra x. Don't need that. Okay, right? Because transformation. I just take this and I put it after one of those x, y's, and the arrow. -x, y. There we go. And then the word description is reflection across y axis. That's the first two already answered. Okay, so now the second transformation is a well, what is it? It's a dilation, right? But it's asking me, like, algebraically. So what do I need? I need to know what the scale factor is. So I could, figure out. Well, first let me see if it is at the origin. It looks like it's at the. That's the easiest way to determine if you have multiple points. Easiest way to determine the point of dilation is to line up all the points, and wherever it intersects at is the point of dilation. Right, so it looks like it's at the origin. Okay, but what is the scale factor? Right, so I could like figure out the distance between here and here. Like I could pick any two of the point pairs. Right, I could do like K and C. Right, and I could figure out the distance between here and here and here and here. Right, or here and here and here and here, and I could compare this distance divided by this distance. Right, it got bigger and it got smaller, so my scale factor is going to be less than 1 because it's a shrink. Right, but I really don't need to do all that stuff. Right, I can look at my change in x or my change in y, and I can look at the two of those. Right, so I'm gonna look at this point and its paired point, which is this point. Right, and I'll do both my change in x and my change in y just to be sure. Right, so my scale factor, it's going to be my my change in x, or it's going to be my x value before or after divided by my x value before, and it's going to be my y value after divided by my y value before equals my x value of h divided by my x value of b, or my my y value of h divided by my y value of b. Okay, so that's going to be 2 my x value is, what am I doing? I'm looking at my x value is 2 my x value before is 2, and its after is, actually after, sorry about that, is 1 divided by 2 equals 1/2. Okay, my y value before or after is 2.5. 2.5. 2.5 divided by 5 equals 1/2. Okay, so they're both, my scale factor is 1/2. Right, so let's see. Yeah, algebraic expression. So should I have a second transformation of this? Right, it's going to be, this is a dilation of, or with scale factor of 1/2 about point 0, 0, or you could say about point of origin, whatever. Then the algebraic expression would be x comma y is 1/2 x 1/2 y. All right, so there you go. And explain if the sequence preserved distance, no, a dilation occurred, therefore all line segments are not the same length as they were before the transformation. I don't know why I put an X there. Right? There we go. Therefore, line segment. Now I'll just say, therefore, distance was not preserved. Or distance between vertices are not preserved. There we go. So that's how you do all that stuff. All right, so for number 2 here, well, I guess the second page. All right, so we have that x through q. X through q is a result of a transformation. So this was your pre-image. This is your image of a sequence of transformations. So I'm gonna make this burgundy. This is your image. That's your image. Okay. All right. These two people wrote sequence transformations, but they came up with a different sequence. Complete the table to see what's missing. All right. Well, a written description for a rotate about the origin, right? This is asking for, let's see, written description and algebraic descriptions. All right, so, well, this is pretty easy, right? And now this is, okay, so it looks like this one's missing an algebraic description, and this one's missing a written description for the first and second transformations. Okay, so rotation about, we'll call the second transformation an orange one, the first transformation an orange one. So rotate about the axis of 180 degrees. Well, if you remember from earlier, x comma y equals x's and y's stay the same for a 180, but both of them flop. So that makes sense. So that means that this is going to end up over here and like rotated, right? And then this is a translation. Anything with a plus and minus in there, that's an obvious translation. That's a translation. 4 to the right, and 3 down. Okay, and then Nathan's written description was rotate about the origin 180 degrees about the origin, and then this is a translation. This is a translation. What's going on here? Oh, okay, it looks like they're just doing the transformations, or just doing them opposite, and they're just showing the same thing out twice. they're just doing them in different order. They're showing you guys commutative property. And this translation. Oh, okay, yeah. So translation of 4 to the right and 3 down. Okay, so both sequences are correct because this is one of those things that I'll show you. Okay. All right, so let's do Julien's sequence. Let's do a rotation of 180 degrees. This is what I think is correct. So let's see if I'm correct, because I filled in what these things are, and I think both of them are going to be correct. All right, so let's take for rotations. I always like to do a coordinate pair table. All right, so we have J, R, T, L. That's a 7, not an L. L. Okay, and the original numbers for pairs are 2 and 6. R is 4 and 4. T is 3 and 2. And L is 1 and 1. All right, coordinate pair comparison is negative x, negative y. All of these are going to turn negative. So now I'll just transpose them. 2, 4, 3, 1, 6, 4, 2, 1. I'll plot them. Okay, so negative 2, negative 6 for J. Negative 2, negative 6. I think it's like right here-ish. Negative 2, negative 6. Kind of hard to do on this paper. That's J prime. Negative 4, negative 4. It's like right here-ish. Okay, that's R prime. Negative 3, negative 2. It's like right here-ish. That's T prime. And then negative 1 is like right here-ish. That's L prime. Connect the dots. Okay, so it's rotated. Looks like it's oriented the same as these two. And now I have to move it. It says +4 and it's got to move. Pause this for a second. Okay, so then if we took that rotation and we went +4, 1, 2, 3, 4, and -3, we'd end up down here right now. So Julia's, I don't think, is right. But let's see if Nathan's is right. Because I don't think Nathan's is right either. I think this is a wrong book issue. Right, so let's see if I take, maybe I'm wrong. We'll see. I could be wrong. But that's why we check it. Alright, so now let's move this guy down. Let's move him +4 to the right. So now for this one, I'm going to take, this is Julia's. Now for this one, I'm going to do it +4 and then -3. All right, so 2 + 4 is 6. 4 plus 4 is 8. 3 plus 4 is 7. And 4 plus 5 is 4 plus 5. 4 plus 1 is 5, right? And then we have 3 minus 6 is 3. 6 minus 3 is 3. 4 minus 3 is 1. 3 minus 2 minus 3 is negative 1. And then 1 minus 3 is negative 2. So I'm going to check these in my mind real quick. Okay, so now I'm going to plot these. Right, so we have negative 6, or we have 6, comma 3. Six comma 3. Okay. We have 8 comma 1. And we have 7 comma negative 1. We have 5 negative 2. Okay. I think I was wrong initially. That's why we do it. Alright, so this will be J prime, R prime, T prime, and L prime. So Julia's was not right. This is Nathan's. All right, so now let's do an x, a negative x, negative y point comparison on this one. Okay, so it's going to be negative, 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 negative. So it's going to be negative 6, 8, 7, and 5. And then our y coordinates will be negative 3, negative 1, 1, and 2. Okay, so let's see if that is right. Let's see, 5 and 2. Okay, so negative 6, negative 6, and negative 3. That checks. Negative 8, negative 1. That checks. Negative 7 and 1. That checks. And negative 5 and 2. That checks. Alright, so Nathan's sequence is correct. So only Nathan's sequence is correct on this one. So there you go. So can't presume things. They're not commutative. Because Julia's sequence was incorrect. You can't do a translation and then the rotation. You had to do, or the rotation then the translation. You had to do the translation and then the rotation. So you couldn't do the rotation and then the translation. You had to do the translation and then the rotation. This was frowny face. This one was smiley face. So, all right. Well, that's the whole extended version of the lesson, and I hope that worked out well for everybody. So from this, you should have got an understanding of how to represent a sequence of transformations on a map or on a coordinate plane, and describe a sequence on a coordinate plane. Identify the transformations that preserve distances or don't preserve distances, and then have a better understanding of the commutative property, and then be able to answer these questions to yourself. Okay, hope that worked out and helped everybody, and we'll move on to 4.6.5.